In keeping with our theme of derivatives, guess what? We're going to add another rule to our set of rules, right? So we know the power rule, we know the product rule, we know the quotient rule. And so today we're going to add the chain rule. So if you noticed so far, right now we've only been able to find f prime if f looks like this, right? Like it's x squared plus 1 or just the square root of x. We can change it to x to the 1/2. But we've not done anything that looks like this with the composition of functions, right? I have one thing inside of each other. F of x is the quantity x squared plus 1 to the 5th, or f of x is the square root of something more than x, right? The square root of 3x minus 2. And so we need the chain rule, which basically says, well, first of all, if y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x is differentiable, and this is the derivative. So when I have a composition of functions, f composed with g, or I mean, that's what this is, right? G is inside of f. Then the derivative is f prime with g inside, I'm missing a parenthesis there, times g prime of x, okay? So it's kind of so this idea here, now I'm going to break this apart for a couple times and then it's better if you can get used to not doing this every time, but this is a good first way. So I'm going to call this y equals u to the 5th, and I'm going to define u as x squared plus 1, okay? So I'm going to use my Leibniz notation in this case. So the way that we use Leibniz notation is we do d, the name of the function, over d, the variable. So this is dy du. So dy du, right, I can use the power rule on, it's 5u to the 4th. Now, what about this thing here, right? This is du, the name of the function, over dx, the variable, and this is equal to 2x. Now you may notice when I multiply dy du times du dx, up here, right, I have dy du times du dx. These u's, the du's, simplify, and I get dy dx. So this is our chain rule. So if I put these together, dy dx is 2x times 5u to the 4th. Now I started out in terms of u and not in x, so I'm going to replace this. Dy dx is equal to 2x and then times 5. My u is x squared plus 1 to the 4th. And then one last step just to make it a little simpler, I can write it like this. Okay? So this is the chain rule. And so I can pull this 5, kind of the shortcut. Okay, so I have 5, so I want to think of this as a big x squared. I pull the 5 down in front, I get this still to the 4th. Okay, so I'm going to do it the other way. I'm just going to show you. I get the same thing. So if I think of this as big x to the 5th, then the derivative is 5x to the 4th. This still stays inside. And then the last part is I take the derivative of the inside. The derivative of the inside is 2x. And so when I multiply the 2 and the 5x, I get, again, the same exact thing. So that is our chain rule. Okay, so let's do a couple of examples. All right, so I'm going to rewrite this first of all as x squared plus 1 to the 1/2 power. So my y prime will be equal to, the way this works is it's like a general, we call it the general power rule, is we just take the derivative of the outside, right? We ignore this in here basically, okay? So we just have like u to the 1/2. So the derivative would be 1/2 u to the negative 1/2. So I'm going to have 1/2 to the negative 1/2. This stays inside. And then my last step is then to multiply by the derivative of the inside, which is 2x. All right, so anytime I have a composition of functions, I'm using this idea. G prime of x is equal to, okay, so again, I want to think of this whole thing, right? It's just like x to the 3/2. So the derivative of x to the 3/2 would be 3/2 x to the 1/2. So I have 3/2. This does not change. It stays the same on the inside. Then times the derivative of the inside. So now I ignore everything except for the inside, and that it's going to give me 3x squared minus 8x plus 6. And that is my g prime. So we are going to continue to use our chain rule on another example here. We have m of x is equal to the cube root of x squared minus 1, the quantity squared. We want to find all points on f for which f prime of x does not exist, or where f prime of x is equal to 0. And so the first thing we're going to need is our derivative, and we're going to rewrite this first. Okay, so let's rewrite m of x is equal to, we can write this x squared minus 1 as a power. So I have power over root, so it's the 2/3 power. Right, so perfect example, we need the chain rule for again. So I have m prime of x is equal to, okay, so first thing, I'm kind of ignoring this thing in the middle here, and I'm thinking, okay, I have x to the 2/3 power. So the derivative of that would be 2/3 x to the negative 1/3, right? 2/3 minus 1 is negative 1/3. This stays the same in here, nothing changes. And then I multiply by the derivative of the inside, g prime. So this is my inner function. So the derivative of that would be 2x. All right, so now to figure this out, now I need to do a little bit of work with my exponent here. So I want to remember, first of all, that when I have a negative exponent, it really means that x squared minus 1 to the positive 1/3 is just means that it's in the denominator. So this whole factor, because it's raised to the negative 3rd power, belongs in the denominator. Right? The 2 and the 3 go here, right? That's 2/3. And then the 2x we can put in the numerator. All right, so the easy one to find first is where is m prime of x equal to 0. So we plug in 0 for m of prime. And we have 4x over 3 times the quantity x squared minus 1 to the 1/3 power. I'm going to multiply both sides by this denominator, right? So I'm going to multiply this and this. Both, this side becomes 0, this side becomes 4x. And I end up with x is equal to 0. All right, so that's my first part. So f prime of x is equal to 0, f prime of 0 is equal to 0. Okay, we'll find the point here in a minute. Okay, so where it's undefined, well, things are undefined when the denominator is equal to 0. And so that's f prime of x does not exist when this denominator does not exist, right, is equal to 0. I can divide away the 3 from both sides, right, and I still get 0, so I'm going to get x squared minus 1 equals 0. So whenever I have 0 over here, I'm going to divide both sides by 3. It becomes 0 over here, it goes away over here. I'm going to raise both sides to the 3rd power. I get 0 over here, and I get x squared minus 1. And so this will be undefined when x squared equals 1, so x is equal to plus and minus 1. So I have 3 different places. So f prime of 1 does not exist, and f prime of negative 1 does not exist. Now it said points on f, and so let's come back up here and look at m. Actually, oops, I called them f instead of m, so I'll just change these. Sorry about that. So my m of x is, I'm going to use this one, I'll just rewrite it down here. So m of x is, I'm going back to my original function here because that's where I find my point values. So I'm going to plug in 0. So not m prime. M of 0 is negative 1 to the 2/3 power, and that will become positive 1. Because the cube root of negative 1 is negative 1, but then when I square it for this part, I end up with 1. So I at 0, 1, I'm going to get, my derivative will be 0. And then over here, when I plug in 1 or -1 here, I'm actually going to get 0 here, right? So m of 1 is 1 minus 1, which is 0 to the 2/3 is 0, and m of -1 is also, because I square it and I get is equal to 0. What we actually find if you go online and graph this is that this has kind of comes to sharp points at these places here. We get a little bend. All right, so let's do a couple more chain rule derivatives. This time we're going to involve some other rules here instead of just the straightforward ones. So this is an example where I could use the quotient rule, okay, but I really don't want to. So the rule of thumb is if I have the numerator is just a constant, then one way to do this is to rewrite this as -3, 3x plus 4, then to the -2 power. Now, sometimes with a quotient, if I had other variables up here, if I had 3x squared plus whatever, you could write them next to each other and use the product rule with the -2, but I recommend that you only use this where you bring up this factor and write it to the negative power when you only have a constant in the numerator. Okay, I highly recommend that. So g prime of x will be, okay, so this time I have the -3 is just a constant, so it sits here. Right, so it just sits there, and now I'm going to deal with this. So this is like u to the -2, right? And the derivative of u to the -2 would be -2 u to the -3. And so this will be times -2, then here's my u to the -3. And this does not change inside. Now, one last thing, right? I have to do the derivative of my inner function. And so my derivative here is just 3. Right, so my g prime of x will be, so I can't multiply anything that's in an exponent that's different than it, but I can multiply this -3 times this -2, get +6, and then also multiply this by the 3 as well. And so this will be 18, and I can write this back in the denominator as 3x plus 4 then cubed. Right, that's a good way to write it, especially if you're evaluating it at certain points. Okay, so again, let me say, it's a good technique to use if the numerator is just a constant, because then you can use the right when it's just a constant on top, then the constant multiplier rule applies. Because if this had an x in it and I wrote it like this, then I would need to use the product rule, and that gets really confusing, I think, when you use too many negative exponents. All right, so we'll move on to the next one. So this time I have f of x is x squared times the square root of 4 minus x squared. So my first step is to rewrite it whenever I see a radical. I'm going to write this as 4 minus x squared to the 1/2 power. Now this time I'm going to have to use the product rule is first, right? I'm definitely going to need the chain rule when I get to the derivative of this part, but the product rule is the first rule that's applicable here. So f prime of x will be equal to, so I'm just going to write it out. The derivative of this will be first. It doesn't have to be first. I'm just using it because I'm going left to right. So the derivative of x squared is 2x, then times this, right? That's how we use the product rule. Says, right, f times g prime is f prime g plus f g prime in either order, right? So this time I'm using x squared as my f, so I have f prime times g, and then plus, then x squared. This time I'm going to take the derivative of this term here. Again, right, this is like my inner function. The derivative of the outer function will be 1/2 this to the -1/2. And then the inner function, 4 minus x squared, the derivative is minus 2x. Again, I say just leave things alone. Don't simplify them for right now, okay? I could make it a little bit cleaner, but I don't want to do too much because it's easier to grade if I can actually see what you're doing as opposed to trying to figure out where you went wrong with your algebra. Actually, I'll make this minus just because I can pull this minus all the way out to the front. This 2 and this 2 can simplify, and I can multiply this x times this x and get x cubed times 4 minus x squared to the -1/2. Really, this is fine. You know, this would be great, and then just leave it from there. So f prime of x until we get to at least to a different part. Right now we're just learning how to use these rules, and that's the priority. All right, so another one. So this time I have a quotient. So I have a quotient rule involving a chain rule. So my first thing I'm going to do is rewrite, because I see a radical. So I have x squared plus 16 to the 1/3 power, because this is a cube root of x squared plus 16. Power over root, power is implied, it's 1. All right, so y prime is, I'm just when I have f divided by g prime, and you do have to memorize this, it's g f prime minus g prime f all over g squared. Right, and I could write f prime g and f g prime. The order of these, the multiplication doesn't matter, but the order that it has to be the bottom times the derivative of the top has to go first. All right, so the bottom, which is, so if we call this f and this g, so I have the bottom, which is x squared plus 16 to the 1/3 times the derivative of the top, which is 1, minus, I don't really have to write the 1, I'm just doing it for good practice, right? So then I have I'm just writing f first here, so the top times the derivative of the bottom. The derivative of the bottom, right? So I just ignore it. I'm just taking the derivative of it where it stands. The derivative of x squared plus 16 to the 1/3. The outside piece is 1/3 this to the negative 2/3. So I have 1/3 times x squared plus 16, then 1/3 minus 1 is negative 2/3. And now the derivative of the inside, derivative of x squared plus 16 is 2x over the denominator squared. So I get x squared plus 16 to the 1/3 quantity squared. All right, so again, I would leave it, I would like it if you would actually write it as, so I'm going to drop this 1 in the first term, so x squared plus 16 to the 1/3, and then I have minus, I can put all the terms not raised to this weird power together, so this would be x squared, and then 1/3 times 2 is negative 2/3 x squared plus 16 to the negative 2/3. And then I would really like it if you could write the bottom as x squared plus 16 then to the 2/3 power, because if I raise 1/3 to the 2/3, then I end up, or if I raise 1/3 to the second power, this is when I multiply my powers together and I get the 2/3 power. So this is really all I need for you to do for that right now. Okay, and really up here is really okay, just this is a little bit neater. Okay, so another one. Okay, so probably maybe the most complicated, the one that we have so far. And so this one is a chain rule first, right? The big outer function is really kind of like x cubed, right? And the derivative of x cubed is 3x squared. And so my y prime is going to be 3x squared, right? This thing inside here stays exactly the same. G never changes inside. Now I need g prime, and guess what I need for g prime? So g is my inner function, and my inner function is a quotient, so I need the quotient rule. So now I need to multiply this by the quotient rule using this. And so that is the bottom times the derivative of the numerator, which is 2. Right, so I'm just strictly looking at the inside, this 2x minus 1 over x squared plus 6. Then minus, now I have the top times the derivative of the bottom, and the bottom is, the derivative is 2x over x squared plus 6 quantity squared. And so there is my derivative. So watch the interplay of all the rules, right? You kind of have to figure out which one applies first, right? This is the outer function is here, so that means the chain rule goes first, and then when I do the derivative of the inside, then I have a quotient rule. Okay, so you're going to see lots of examples where they're sort of intermingling like that.